Hello, welcome to the Chemical Reviews Thematic Talk Series. I'm Sharon Hamas-Schiffer, the Editor-in-Chief of Chemical Reviews. And today the topic is machine learning at the atomic scale. This issue was just published in August and features a wide range of exciting reviews on both methods and applications of machine learning in chemistry. It is my great pleasure to introduce Michele Schieriotti, one of the guest editors for this thematic issue. He will present a brief introduction followed by 4 talks presented by authors of reviews within this issue, and we will then have time for questions after each talk. Please type your questions in the Q&A using the prompt at the bottom of your Zoom screen. So Michele, go ahead with your introduction now.
So I hope that the screen sharing is working, and welcome everybody, and thanks to the speakers who agreed to participate, and to Chemical Reviews for organizing both the special issue and this thematic talk event. So I've guest edited the special issue together with Anatol von Lilienfeld and Cecilia Clementi. And before introducing to you the speakers, I just wanted to mention that this special issue contains 11 papers covering many different aspects of the application of machine learning techniques to chemistry, and in particular to the problem of atomistic simulations of chemistry and materials. And so we had to really pick the best of the best to introduce to you a broad overview of the topics that are covered in the special issues, but there is much more, and I invite all of you to go to the Chemical Reviews website and download the entire special issue. So today we are going to start with Cecilia Clementi from Berlin. And she's gonna tell us about unsupervised learning methods for molecular simulation data. And in fact, Cecilia has been working, applying dimensionality reduction and methods that we would now classify as machine learning to the modeling of biological systems from long before it was as trendy as it is today. So we really have a pioneer in the field of the application of machine learning to biological simulations. Our second speaker, another pioneer by many accounts, is Professor Gabor Csanyi from Cambridge, who is going to present in particular Gaussian process regressions for materials and molecules. And I think that particularly for the case of the application to materials and the construction of interatomic potentials, Professor Csanyi has been really the one who has brought Gaussian processes and kernel methods in general into the spotlight for application to materials. And something that really characterizes his work is the effort to understand the interplay between mathematics, the mathematical structure of the problem, the underlying physics, and the application to problems in material science that are hard to solve. As a third speaker for today, we have Klaus-Robert Muller, also from Berlin, who is going to talk about machine learning force fields. And Professor Muller is really a computer science person, so he is really he's a regular at NIPS or New RIPS, as it is called nowadays, and he's really a big name in the field of machine learning, and I think it's fair to say that he was one of the first, if not the first, from that field who saw the potential in the application of machine learning to chemistry, and ever since has been really acting as a bridge between the computer science machine learning community and the community of computational and theoretical chemistry. And as the last speaker of today from Cambridge, Massachusetts and MIT, we have Heather Kulik. Professor Kulik is a chemical engineer, and she is perhaps the most applied on the palette of the presentations that you're going to see today. And Professor Kulik is really, in particular, interested in the design of catalysts. And lately, she has been incredibly successful in using machine learning to extend the reach and the depth of what can be achieved in terms of the computational discovery of chemicals and materials. So without any further ado, I will basically stop sharing my screen and pass control to Cecilia. Please, Cecilia, the floor is yours.
Right, I'm happy to introduce Cecilia Clementi, who will talk about unsupervised learning methods for molecular simulation data. Thank you, Michaela.
I'm not able to share my screen. One second. Screen. You see my presentation?
Yes, we can see it. Yep.
Yes.
Okay. Thank you very much for the introduction. And today I'm going to tell you about unsupervised learning method for molecular simulation data. So I want to start by reminding you that traditionally molecular dynamics and quantum chemistry have been the workhorses in computational chemistry. Basically, if you want to study something computationally in chemistry or in chemical physics, you always start with it's very difficult to get around these methods. Today we add machine learning to the toolbox, but traditionally these have been the two workforces. And what can we do with this kind of tools? Well, there is a very large range of applications we can apply these methods to, that go from the understanding of principles up to the very practical design of, for instance, vaccines or solar cells or batteries and so on. If you want to do this computationally, you use molecular dynamics or quantum chemistry or a combination of the two. And today I'll focus on the molecular dynamics side. I'll talk about what we can do with molecular dynamics. I think all of you know what molecular dynamics is, but just a brief reminder. Basically, you have, and I'll talk about biomolecules. Molecular dynamics doesn't have to be applied only to biomolecules, but biomolecule is my expertise, so I'll talk about biomolecules. For instance, in a protein, you have 20 different amino acids. You have a sequence of amino acids that makes a protein. So you have a chemical composition, and you assign a certain energy function for each particular interaction between the atoms, depending on the atomic species. And then you integrate this equation in a computer. You have an energy, and then you take the derivative, you get the forces, and you integrate Newton's equation of motion in a computer. And this is very simple, but it's very powerful. And nowadays is used for, as I said, drug design, material design, and so on. And this has been pioneered by people who got the Nobel Prize for their work, like Levitt, Varsher, and Karplus. And so since this is to show you that molecular dynamics is a very mature field. It's been around for a long time and is pretty established field. But what has been more recent is what to do with molecular dynamics, besides making pretty movies. How do we go from integrating the equation of motion to prediction, for instance, of a drug, designing a drug, or prediction of certain property of a material? So there are three challenges for that. One is the design of force field, and Klaus will talk about that later. One is the sampling, the fact that we need to have a good sampling of the configurational space of a molecule to be able to do something about it. And the other one is the data analysis. Even if we have a perfect force field and we're able to sample, as I'll show you, we still have to do something with the trajectories with that. My work is on all these areas, and lately I'm applying machine learning to all these areas, but today I'll focus on the data analysis part. So this is the general pipeline. What do you do with the molecular dynamics data? So you start with the trajectories. That is really the coordinate, Cartesian coordinate of the molecule as a function of time. So you have x, y, z for all the atoms at all the different time steps. You transform this coordinate into something else, something that is more amenable or more representing, for instance, the symmetries of the system and the properties of the atoms and so on. And then you usually do some dimensionality reduction, and you end up with something like an energy landscape, a free energy landscape that you get through an energy density estimation, or some sort of state and connection between the states. Why do we want to do, how can we do this, and what is the physical rationale for doing this? Well, usually we look for slow processes. What does it mean? That usually, or we hope that usually, there are processes separated by different time scales. That means that there are slow processes, like here I'm showing an helix coil transition in a biomolecule. You have the reconfiguration of the coil or the vibrations in the helical state that are very fast, but the transition between the helix and the coil are very slow. They happen very slow, meaning very rare. They happen fast, but they happen only once in a very long while. So you spend a lot of time in one state and then you jump into the other one. So what is interesting is to find the state and find what is the collective coordinate or the reaction coordinate that connects this state. So one question, how to analyze molecular dynamics data, how we can extract these collective variables associated with the barrier crossing events. This is a slide I borrowed from Michele several years ago, and to show that the question of reaction coordinate collective variables is not just in biomolecular system, is basically pervasive in many areas of science. In order disorder transition, we look for an order parameter that tells us where we are in the transition. In material science too, we want a coordinate that tells us, it gives us information on the specific process we are focusing on. And in biomolecule, we want a coordinate that tells us, for instance, if we are in a given state, in a given conformational state or another. It can be identified by beta sheets or alpha helices. Because this question of reducing the dimensionality, of finding important collective variable and so on can be rephrased, are very similar in different fields. Over the years, we have followed the lead we followed the example of what has been done in, for instance, image recognition, and used the same algorithm. And when machine learning has come in fashion, we have jumped on it because clearly this is a good way to answer these questions. So what do we want to do, and how do we achieve it? We want to get slow processes and the states that are separated by the slow process. In the example I've given you before, we want to get the two minima that correspond to free energy minima that correspond to the helical state and the coil state, and the coordinate that connects them, or some rate of interconnection between them. And we want to extract this from trajectory, molecular dynamics simulation. Let me give you a one-dimensional example. If we have this energy landscape in the top figure, there are clearly 4 minima. This is one-dimensional, so we can visualize and see that there are 4 minima. If we plot the probability density, we have 4 maxima. And if I ask you how many states you have here, you can say 4, because there are 4 minima. One is the deepest, then there is the second one that is comparable, and the other 2. And you can do this because you can see it for minima. But we want to do this for systems that are very high dimensional, where the energy is given by this combination of energy terms that are very nonlinear. And it's impossible to visualize it. You cannot just plot something in 1,000 dimension or so. So we need some tools to extract this information from the data. We want to extract the position of the minima and the rate of the interconversion between them from the data. This is an example. This is a rough free energy landscape, and this simulation changes color every time the molecule jumps in a different minimum of a landscape. The landscape is not this one. This is just in 2 dimensions. This is an higher dimensional. And somehow we have extracted this state, and as you see, the simulation, the molecule jumps into another conformation and fluctuates around this conformation. This is a post-analysis thing. The analysis has already been done. Another example is this nice paper that was published in Life a couple of years ago by John Chodera and other people. This is a molecular dynamics simulation of an enzyme. You are interested in the catalysis of this enzyme, and you can see there are very large movements. That in particular, the areas colored are undergoing very large conformational changes. But we can stare at these movies as long as you want, but it's not quantitative. You cannot tell an experimentalist, this is where the catalysis is happening, this is the rate, because this is just a movie. What you want is something like this, where in addition to the movies, you have decomposed the simulation in states, and you can visualize the states, and you can say this is the most populated state. When the conformation, this conformation corresponds to this state, this is the rate of interconversion between the different states. And different states may have different biological meaning. Biological, for instance, one can be active, one can be inactive, and so on. Let me go back quickly to the one-dimensional example. I want to tell you how we do this in practice. There are many ways to do this in practice, and this is what this article in the Chemical Review issue we have written describes. But I'm going to give you one way. That is the spectral method. Basically consists in finding eigenfunctions and eigenvalues of an operator that can be characterized, that characterizes the dynamics, that can be a numerical approximation of this operator can be obtained from the trajectories. And what you get is something like this, is an eigenvalue spectrum. And the presence of this gap tells you that there are 3 processes that are slow and everything else is fast. 3 because the first one is always 1 and is trivial. The first eigenvalue corresponds to the existence of an equilibrium distribution, and the eigenfunction is flat, and so it corresponds to the equilibrium distribution. But the first eigenvalue, the first interest eigenvalue corresponds to, you see the eigenfunction changes sign here, and this corresponds exactly to the position of the first barrier, the largest barrier. So it divides the space in 2 parts that are separated by the largest barrier. This next eigenfunction gives you the position of the next barrier. And the last one, the position of the last barrier. So these eigenfunctions give you the perfect space to look at this system and to find the minima. So this is a way of one powerful way is called Markov state modeling. That is to analyze molecular dynamics simulation data. There are many other ways, and then always following the same idea of extracting some free energy profile or some state decomposition from the data. This is, just to conclude, I want to show you an example of what can be done in practice with this. This is a simulation that was done in Frank Noy's group, another author of the review. And this is a massive simulation. This is 100 microseconds of molecular dynamics data. And you can see this is the association of 2 proteins, Barnase and bar star. And you see that they associate, they dissociate, they reassociate, and so on. What do we extract from this? If you apply these techniques, you get something like this. This is the Markov state modeling. You have associated states, you have bound state, and you have dissociated states. And beside this state decomposition, you can have free energy profile as a function of some reaction coordinate. And then this is not just for the sake of it. This is because with these tools, if you do these, you can compute observables, like for instance, free energy differences between these states. And then you can compare with experiments. For instance, you can do something like this, as it was done in this paper. You compute delta G's for mutation in simulation and experiment. You can do it because you have free energy landscape, or you have this state decomposition, and you find, you predict or you validate your study against experiments. With this, I think I've already abused of my time, so I want to remind you that this is the review we have written for the chemical review issue, special issue on machine learning. And why I didn't mention explicitly machine learning, but all of this is it's called shallow machine learning because it's extracting information from data. So far, I've talked about shallow method, but all of this can be done also with deep methods like neural networks and so on. This is the foundation which this method can be applied, and all of this is described in our review. With this, I would like to thank my group and all of you for your attention. Thank you.
Thank you very much, Cecilia. Also, actually, because of my timer, you are concluding at 15:10, so perfect. We have already a question. So anybody who wants to ask questions to Cecilia, please type them in the Q&A box. We have already one, so I will read it out for you. From Zrabani Tarapter. The question is, for the kinetics of Bernays-Bar-Star association, how do you decide how many states to consider in the network?
This is in general, this is not just for the Bernays-Bar-Star association, that by the way was not my study, was from another group. You look at the spectral decomposition. So if I can go back here, you look at the spectrum, the eigenvalue spectrum, that is always one dimensional. You have the eigenvalues and their values. And you look at the gap. You want to find a large separation between some eigenvalues that are close to 1 and some eigenvalues that are close to 0 as much as possible. If you find this, this is a good space, it's a good place to stop. And you take the coordinates corresponding to the largest eigenvalue, and you do the decomposition in that space with the number of states that is corresponding to the number of eigenvalues. But not always you are so lucky to get a large gap. So in these cases, you need to use other criteria. For instance, we have published papers a few years ago suggesting to use more sophisticated methods and get the variance, like to see this coordinate, how much of the configurational space they can explain, how many processes they can explain, and you can get like 90% of the processes are covered by, I don't know, the first 10, 15, 20, and then you can use these variables for the decomposition. I mean, the answer is look for the gap, but the more complicated cases need to be dealt with more special methods.
So very, very quickly, there is a follow-up question, which is what would be the dependence on the length of the trajectory?
Okay, that's a good question. If the trajectory is long enough, you have an equilibrium sampling, meaning that you have a representation. If the trajectory represents the Boltzmann distribution, samples the Boltzmann distribution, and you can apply this method straightforwardly. If the trajectory is too short, or if you combine many short trajectories, you are not going to have a good sampling of the Boltzmann distribution. You can sample it, but not in equilibrium. You have an out of equilibrium sampling. And so this method assumes that you have at least local equilibrium. So you need to reweight and you need to combine trajectories with more sophisticated methods, and you can look at this in the reviews, in the review we have published, and following the references there.
Thank you, Cecilia. There is one more question, but given that we are a little bit tight on time,
I'll type the answer.
I would suggest you type the answer. So thanks again. Let's. Unfortunately, we cannot clap loudly, but I'm sure everyone is very clapping in their head. So thank you, Cecilia. And
I'll stop sharing.
Yes, please. And I would invite Gabor to share his screen.
Right. So the next talk is Gabor Csanyi, who will talk about Gaussian process regression for materials and molecules.
Oh, do you see the slides? Good.
Yes, we can see the slides. Yes.
Okay. Let me just rearrange some windows. Okay. I'm ready. Good. Thank you very much for the invitation, of course, for this event, but as well as for writing the reviews in this excellent, fantastic issue of Chemical Reviews. I will actually try, and I left the name of one of the reviews as the title because that's in the official program, but I will actually talk about the interplay between two different reviews, one of them organized by myself and the other one organized by Michele Ceriotti. So I'd like to give the technical details are in the reviews, and I'd like to spend these 15 minutes to talk about the concepts and the motivations of this work. So we'll essentially pick up the thread from the first part of Cecilia's talk, which is the potential energy surface. Everything that she talked about relies on defining some kind of potential energy surface and doing molecular dynamics on top of that. So how does that fit into the multiple scales of modeling, the different tools that we use to understand the chemical physical world around us? So this is a slide on which people can usually place themselves or their interests. You see a very wide range of capabilities on the x-axis. So in terms of atoms, we go from quantum chemistry, essentially an exact solution of nuclei and electrons, all the way to coarse-grained molecular dynamics, or even continuum methods where we treat very large systems. But on the y-axis, of course, I have provocative numbers and words for accuracy. These different models on these different length scales do not capture the systems that we study exactly. And as you go to higher length scales and larger numbers of atoms, of course, you become less and less exact. So how are these models parametrized? So at the top end, typically you have some theory or of how things work. You make a model and then you test it against experiment, typically, or some sort of physical limit, some idea of the macroscopic behavior of the model. And that is how people make coarse-grained models, and that is typically how people make empirical force fields. So you posit some functional form, you have parameters, and then you run simulations and test them against what you should be getting. But of course, the last few decades has seen the rise of a completely different way of modeling atomistic systems, and that's I would call that just generally first principles modeling. It's more of a deductive approach that you start from the bottom. We know how quantum chemistry works. We know the equations. And for larger systems, we can't solve them exactly. So we make principled approximations through quantum Monte Carlo, use a stochastic method, or density functional theory, where we try to create density functionals, exchange correlation functionals that capture the real solutions in some mean field sense, all the way through to empirical quantum mechanics. So if you look at the literature, this idea of first principles modeling, although it is an approach, actually it's more or less synonymous with electronic structure calculations. So it sort of stops, this idea stops here. And more to the point, if we can understand why that is, if we look at what the objects of study are. So up to this stopping point, we have wave functions, an electron density, some form of electronic description. Whereas beyond this stopping point, we have atoms and molecules. But if we look at how the world, what people actually do with these models. How is computing time spent? If you look at the largest use cases of supercomputers, a lot of time is spent on something called first principles molecular dynamics. And that's a strange thing to do, because it's molecular dynamics, but not on the atomic scale where the objects are atoms, which is what people should be doing, but actually running quantum chemistry, but discarding the wave functions and the electrons and so on, and propagating only the atomic positions, right? So it's sort of doing something that we want to do, molecular dynamics, but at using, in some sense, the wrong tool, something that's much too accurate, much more fine-grained. And the reason is that the first principles approach has had a barrier. And the work that I'm describing to you, and the work that's detailed in the two reviews, is really about breaking down that barrier. So extending first principles modeling, this deductive approach, all the way up to molecular dynamics, to atomistic systems, and perhaps beyond. And we do that by creating systematic, principled approximations, potential energy surfaces to the quantum mechanics that has served us so well all the way from quantum chemistry to empirical modeling. So what has happened in the past 15 years? There have been a lot of rooting around for solutions and a lot of applications. Myself, my own group work on the material side. Of course, lots of things happened on molecules. I'll leave that for Klaus's talk, but it started with things like carbon and silicon, which are more simple elemental materials, and yet certainly when you go to the amorphous phase, pose very difficult modeling challenges. But of course, since then, we've done boron, phosphorus, elements for which there really haven't been any empirical force fields, because their chemistry is just too complicated. And then later on, oxides and things like iron and sulfur at Earth core conditions. So systems which are much more complex chemically, and for which molecular dynamics models, force field models, really have not been part of the modeling tool. But how did this happen on the modeling side? So I would say that there was this dark room where people have been rooting around, picking up different tools, understanding the tools themselves through using them. Of course, there are the old quantum chemistry tools, analytical modeling of small gas phase, small molecule, potential energy surfaces, the empirical force fields that I've mentioned and what Cecilia has mentioned a couple of times, and the new tools, kernel machines, Gaussian processes. That's what our review is about, but also feed-forward neural networks and symmetric polynomials. So the past 15 years, lots and lots of groups have picked up these tools and did lots and lots of exploratory work. And what I feel has happened over the last couple of years, especially 2020, is that we've sort of understood the interrelationships of these different methods. They've all given good successes. Some of the examples are here on the left, but I feel like I now understand how these methods work in a way that I didn't over the sort of 10, 15 years ago. And let me just illustrate some of these interrelationships. So we arrived at this concept of symmetric polynomials for describing the atomic environments. And now we know that these are like the body-ordered empirical force field terms if you leave out the fixed functional forms. If you let the functional forms of the pair potential, the angle term, the dihedral term to be just general polynomials. We also understand that you get the same sort of description if you take the analytical, the full potential energy fits, like the permutationally invariant polynomial work of Francesco Pesani, Joel Bowman, and those people, and the many body molecular body expansions, and you relax a few things. You do atomic expansions rather than molecular expansions. You introduce cutoffs. You arrive at the same generic model. But we've also understood how the kernels and the shallow neural networks that have been so successful over the past 10 years also can be fit into the same framework, and perhaps also the much more recent message passing neural networks that have found that really are the state of the art in terms of accuracy can also be understood using symmetric polynomials. In parallel to this understanding of regression and how we fit functions, this whole process was conditional on understanding local representations and the descriptors of atomic environment. So now this is the subject of the other review paper, one organized by Michele Ceriotti. And what this picture is from there, and what it illustrates is on the leaves of this tree are all the different ways that people over the past 10 years have chosen to describe local geometry, interatomic, in order to do various machine learning tasks, describing interatomic interactions, or do unsupervised learning about the structures. But all these different descriptors, from sorted eigenvalues of operators to sorted distances to histograms to the permutation invariant polynomials to atomic symmetry functions, all of these things, which look extremely different when you read those papers, look like they have very little to do with each other, have now been understood as just different ways of enforcing symmetry constraints. And through this understanding, we can actually put them on the same footing. And it turns out that they're all, in some sense, are many-body correlation-based representations. They can all be understood by thinking about the two-body, three-body, four-body correlation functions of the atoms in a given environment. And of course, this is the ingredient that completes the polynomials as a way of fitting functions. Let me give you just one example of success, which is the most challenging element, is of course the most important element for chemistry, and this is carbon. So this is the example of our recent iteration of our model for pure carbon. What you see here is an illustration of all the different structures that go into this model. So from cubic diamond to hexagonal diamond to amorphous to graphite to nanotubes, fullerenes, very, very large number of structures. And if you want to fit the potential energy of all of these structures very accurately, it is actually a very difficult task, just from the raw point of view of accuracy demand. So to illustrate why that is, think of a carbon dimer. And when two carbon atoms are pushed together, the energy that you want to describe is on the order of EVs. They have a very strong repulsion. So that's one of the energy scales. But you also simultaneously want to describe things like graphite and the very weak van der Waals coupling of the different graphite layers. So on the right-hand side, I show you the energy per atom of the binding energy of graphite, and you see that it's basically on the order of a few hundreds of millieV. And if you want to describe these accurately, you're looking at describing an energy function of a carbon atom with about 1 part in 10 to the 4. So 1 part in 10,000 accuracy over a very high dimensional space. And this is achievable with about, the way we did it, but of course you can use any of the other techniques too, but about 9,000 basis functions, 6,000 DFT evaluations of small structures, and the kernel machine that does this with the required accuracy on these small structures gives you about 1 million-fold speed up compared to running DFT. So that's the sort of gain, that's the new world, that we can do 1 million times faster calculation with 1 part in 10,000 accuracy for DFT. And here are a bunch of properties, defect formation energies in all these different structures. And you can see that we are hitting the target with an unprecedented level of accuracy. The other gray circles are the different, gray crosses are the different empirical models. They're all over the place. So this is really a new world of force fields in terms of systematic approach and ultimate accuracy. So I'd like to sort of finish up in the last few minutes. Oh yeah, here are the two reviews just to give you a visual clue. So the first one is the title of this talk, Gaussian process regression for materials and molecules. And the other one is physics-inspired structural representations for molecules and materials. And it's based on this that we can do the first, we can do the modeling. So I'd like to leave you just with a few thoughts about current modeling challenges. what's going to happen in the next 5 years. So we think we've solved the short range potential fitting problem in many different ways, which we now understand are actually sort of doing the same thing. The energy here only depends on the near environment. But of course, in many chemical systems, long-range interactions have to be treated explicitly. There are many ad hoc ways of doing that, but to do proper, flexible, polarizable electrostatics, including charge transfer, essentially leading to modeling the self-consistency that's inherent even in mean-field methods like DFT, is still something that people are very actively working on now. One can use the same ideas to do coarse graining. So the coarse grain models that people use now can be put onto the same footing. The accuracy versus cost trade-offs are quite different. So I don't expect that we'll get the million-fold speed-ups with respect to all atom simulations. And then, of course, we can go to lower length scales. So similar ideas, particularly about representations, could play a role when we think about the full electronic correlated wave functions. They have exploitable local structure, and these new representations could be used to escape typical exponential scaling when we do a correlated quantum chemistry. We are also going to have a new workflows in atomistic modeling. So one of them is, we could call it machine learning enhanced ab initio MD. So you take your typical DFT codes, VASP, for example, it already has ML-based interpolators using techniques that are very similar to the ones described in the review paper in Chemical Reviews. This allows extending timescales. Complex chemistry is basically automatic. If you can use these DFT codes, you will get a huge gain in the timescales you can access. Of course, a lot of us are looking to build general force fields for a given application, be that organic systems or some material. And here, how you assemble the range of configurations, how you then fit them, typically iteratively, until the properties converge, and then how you use them in some large-scale MD is something that is going to be basically routine. How do we know these simulations are correct? That's something that I'm particularly interested in. So asking new kinds of modeling questions. The first one, we could call
Gabor, you have really 1 minute.
No, I'll be done in 30 seconds. So given a database of very small structures, how does the accuracy of that fit, which we control with some fitting weights, determine the accuracy of ultimate molecular material properties? We don't have a mathematical, systematic way of answering that question. There is the inverse problem. So how, if I have a given material property, what should I put into my fitting database? And what accuracy should I want in my fit on that fitting database to obtain good predictions of material properties? These questions did not arise before because force fields were not systematic, but they are now. And I'm really curious about how we're going to answer them. Thank you very much. And I'm happy to answer questions.
Thanks a lot, Gabor. And we have a couple of questions in the Q&A, and probably we are not going to be able to answer more, but please type and Gabor will answer typing. So we have first question from Elizabeth Lee, who asks, for different formation energy, it is known the charge state can strongly change the electronic structure and therefore thermodynamic properties. What would be some strategies to take that account within the GAB formalism?
Thank you. Yeah, so this is one of the outstanding challenges, I would say. So the gap and in general these local descriptions give you ways of fitting local quantities. And in the example that you're describing, when you change the charge state, the local geometry for each without changing the local geometry, the energy forces change. So you shouldn't be fitting purely the energy with these methods. So the question is, what do you fit? Do you fit some sort of local projections of the band of the band structure? Do you fit polarizabilities? Do you fit, what is the local thing that you model, which then in some outer loop of charge equilibration ultimately gives you the right answer? I think that there are many different attempts in the literature for this, all leveraging the same local representations, but just using them in a way that accounts for that necessary charge transfer. It's something that I see on my own path in the next couple of years. I would say we're very far from the final answer in that, but what I'm sure that is going to leverage these local representations.
So, Gabor, yes, no question. Are methods such as function fitting and gap compatible with the highly efficient MD codes?
I think yes, the answer is there. We have LAMMPS plugins, and in fact, the parallelization is an excellent because we spend a millisecond per atom locally, and so we can scale to tens of thousands of cores and use hundreds of thousands of atoms in the MD.
Thanks a lot, Gabor. And well, again, virtual applause. And I would invite you to please unshare the screen so that we can hand over to Klaus.
Right, and our next talk will be given by Klaus Muller, who will be talking about machine learning force fields.
You're muted.
Yes. Okay. So it's always the computer scientists who messes up things. But anyway, so it's a real great pleasure to be here and to talk about machine learning force fields. And I thank you very much for the very nice talks that I could listen to, and also for being able to contribute to the special issue in Chemical Reviews. You can see my co-authors, but there are many more. And I would like to start a bit with my plan. I talk a bit about machine learning in general, but I would like to take this opportunity to make a point that IPAM has been playing a very crucial role, the Institute for Pure and Applied Mathematics at UCLA, in fostering this field and nurturing it. So in the program that Anatol von Lilienfeld organized in 2011, that was a bit of the start of a wave. Then 2016, Alex Kachenko and I had the privilege to organize in 2019. It was Cecilia and Frank and others. So thank you to IPAM. It's a wonderful place. Please go there if you get the chance. And there will be, I think, a program coming up next year, organized by Alex Kachenko. So now for machine learning force fields. So, and before that, I would just give you a bit of a introduction to what how machine learners think about machine learning in a very broad sense. So you typically have data, and quite often these days you have a lot of data, which is not exactly what you have in chemistry or materials. You rather have limited data. So that data is then training a machine learning model, and there's two workhorses that have been mentioned before, kernel methods such as Gaussian processes or SVMs, but also deep neural networks. So I had the privilege to have Vladimir Vapnik as a mentor back in the days, and we were among the first to study this, the kernel methods, and I was also doing neural networks since about 32 years. So I have a very close link to both methods, and they are dear to me, both of them. Maybe the difference to just pure interpolation in machine learning model is that we try to predict given data that was from some probability distribution, and we try to predict such that the unseen data that we haven't seen, our predictions still are very good. So it's called the generalization error would be low. So we try to generalize from limited data to everything that we haven't seen. Very similar to human learning, where we only need a few examples and then we can infer the rest. So that's at least the principle. So now about force fields, just to give you a bit of an idea, and luckily Cecilia has already talked about it, and Gabor. So typically you have a molecule, and the molecule lives in a 3n space, n is the number of atoms. And if the molecule does its dance with the molecular dynamics, then basically for every configuration in this 3n space, you could in principle compute an energy or also the forces. So from a machine learning point of view, this looks a bit like estimating a vector field, which is something very common to us in, say, computer vision. So we're very comfortable with that. And so if we now estimate, from some samples, some force field or some energy landscape, then of course the samples need to be reflecting the underlying landscape very well. And that leads to a lot of very important questions that people have been working in chemistry on for a long time, but also in machine learning, that has been a very common question to ask. And so if we now think about it, we can take, for example, a kernel model. So it's also a Gaussian process model, but it's in the derivative space. And this is the equation for the connoisseurs. So assume that we use that. It actually has some very interesting properties. And I would like to make one important point. So assume that we have some potential energy surface, and this is a very silly example. And from that, you sample. So there are some forces, and you would like to actually get the true potential energy surface. But given these few samples, maybe your prediction is like that. So it doesn't resemble the true potential energy surface. But the reason for that is that if you just predict the force, the vector field, without understanding that it's a physical vector field, then you're losing some information. So therefore, if one wants to properly predict force fields, then it's important to understand that forces are conserved in this universe. And so if we have that, a conservation law of forces, it's actually energy conservation is actually something that is a differential equation that highly constrains the possible vector fields. So if we use this constraint, then we can actually have one part of our estimator, which is the conservative part, which is a very good estimator of the force field, and then some other part. And there are some models out there that use constraints that we have about the physics and the chemistry very well. And that is a very crucial thing, as we will see. So because if we take a small innocent molecule, say aspirin, then the typical thing is that the force field needs about 50,000 samples to properly approximate it and predict it. But if you factor in the differential equation here of energy conservation, then practically you can reduce this number of samples to less than 1,000. Now you can go beyond that. You can also consider symmetries of the molecule at hand, and these could be rigid symmetries or non-rigid symmetries. And then the number of data points to achieve the same quality is becoming even lower. So you see that there's easily a factor of 500 between a model that takes into account all the prior knowledge that you have and a model that is ignorant to that. And if you think about it, given that most of these calculations would be DFT calculations, ideally, if you would like to get a very accurate force field, perhaps you would like to be adventurous and just do a lot of CCSDT calculations, which is completely unfeasible for 50,000 data points, but which is very feasible for 100 data points. So the fact that we are taking into account knowledge that we are having, and this way need less data, can be more data economic, is something very important, and where actually machine learning has been playing a very crucial role to get there. And also, I mean, just for you to think about this intuitively, if you have zillions of data points, and for example, companies like Google's do have zillions of data points, then you can essentially infer anything, right? But if you but there's stuff that you already know, and ideally you don't learn the stuff that you already know. Ideally the models will reflect this by themselves, by construction, and you just learn the things that you don't know yet. And so given that, the models, it's a gradient domain machine learning or a symmetric gradient domain machine learning, we could look at many chemical applications, and you can look at some probability distributions and spectra, as you see on the right, and compare the CCSDT quality force field and the DFT quality force field, and you can see that there is something missing in the DFT quality force field as expected. So it means that by using these novel models that take into account our knowledge, we are able to actually go to very high quality force fields, get the ground states right, get the spectra right, get everything to the right order, that it actually finally coincides with experiment. And I think that's a very big step forward and a very useful step too. Perhaps also one remark, you can also take classical force fields, and they are blazing fast and wonderful. But if your application needs certain accuracy, then they are not sufficient. So then this is a very good alternative. It's slower, say in order of magnitude, but it's much more accurate. So if you need the accuracy, then that's a very nice alternative. And you can ask all sorts of wonderful chemical questions and study this. And this is all very nicely explained in our review paper. Now, and there's code available and so on. Now, I've so far talked mainly about kernel methods. There's also, and Gabor also alluded to this, there's a lot of modern neural networks these days. And as someone who actually likes both kind of models, I feel nowadays people often say, just use a neural network, everything else, forget it, right? But that's of course nonsense, because all these methods, they have their applicability, and in the end you want to solve a particular problem, and then you take the tool that is appropriate to that. And sometimes it's a neural network, and sometimes it's a kernel method. Now, if you think about the main difference between a neural network and a kernel method is that neural networks scale well as if we have many data points. That's one point. And also neural network learn the representation of chemistry, which is very interesting because they learn it such that the task that we want to fulfill, predict, is optimally represented in terms of the representation that the model comes up with. Whereas in kernel methods, you would essentially have to think ahead about a good representation, and of course, if you have thought right, then it's a good path. The real interesting development in the neural network field is that you can also incorporate limits, physical limits in the model, or chemical limits, chemical prior knowledge, and also short and long range interaction or equivariance, all sorts of properties that you already know, that you don't have to learn. So that also makes these type of neural network models extremely sparse and data economic. So just to come to a conclusion. So the neural network models, they learn to represent the chemical environment. Kernel methods correspond to a fixed representation that we have to fix beforehand. So including prior knowledge is super helpful. As I showed with SGDML, having to compute 500 times less data is kind of useful for if you do CCSDT. But also in the modern physics, the modern neural network architectures, you can also include physics and priors in all the properties. There has been a lot of work that has been pushing this limit forward. Now, there's also an interesting point. A lot of people, they don't take the neural network or the machine learning method and learn from it. But you can actually learn from these models novel insights, novel understanding, which you didn't know before. And that is a very interesting development. So for somebody who has been doing machine learning for half his life, and I also have a training as quantum in theoretical physics. So I see that there's a very nice mutual transfer between machine learning and physics and chemistry, but also back. And I'm especially happy because the techniques that are able to include physical priors, they can also move back to standard machine learning questions that are not physics and chemistry and push us forward. Then, just to give a bit of an outlook, I think inverse chemical design was something that Gabor mentioned. This is a very important aspect, and I think generative models are very helpful for that. And there's also a very nice article in the special issue. One thing that I find quite interesting is, and we haven't enough explored this, is that we're not only having atomistic simulation data, but we also have experimental data, and they have different, properties and, if you wish, quality. And going into a loop where we can use atomistic simulation perhaps to guide an experiment in some kind of active sampling way, that's, I think, a very rewarding step, and people have started this path already. The one thing that I also want to mention is that currently people are very much after accurate force fields, but when you couple a force field into the MD simulation, then it's also a question of how accurate are you doing your MD afterwards, whether you do path integral MD or something, because you could easily have a very accurate force field and you mess up the MD part by not being, having path integral formulation or so. So, but
we have 2 minutes left and a couple of questions. So if
yes, I'm sorry. So a very important step is to scale to large molecules and non-local and local interactions. This was also learned before, and a very interesting thing for me personally is to learn wave function models. This is a interesting point coupled to DFT codes. Okay, then I'm ready.
Okay, thank you very much for a fantastic talk. Michaela's Wi-Fi is having some issues, so I will handle the question and answer. So the first question is from Pierre, and he asks, what is the form of the force field derived from CCSD and or DFT, particularly compared to classical ones? First, second generation, completely different?
Yeah, I think this is a very good question, and we actually wrote a paper, especially doing quantitatively answering this. So, comparing classical force fields to the CCSDT type force fields, and you could see some of the pictures that I showed were from this paper. So I could, it's in JCP, Huziel Soceda was the first author. I believe it was 2020, right? But essentially you see differences, and that the differences are remarkable, right?
Okay, and the next question is from Elizabeth Lee, and she asks, would machine learning force fields be applicable to larger systems like proteins and polymers? What would be some challenges to extend machine learning force field methods from molecules to larger and softer systems?
Oh yeah, I mean, that's a brilliant question. And we have been thinking about that for quite a while. And I think there's hope to that. So we're not ready to talk about it. But I think, yes, you can go to larger systems, but you have to do it the right way. It cannot be done, by brute force. When one needs to really do something on the chemistry and on the machine learning side. So that's the beautiful thing. Always, if these, I think the beautiful thing in this field is really that both fields need to work together. So they need to be creative on both sides. Then you can make progress. And softer systems, I mean, that's a very important question to all of us these days, right?
Yes, and there's one last question in the chat box that you can answer on reactive force fields. So I think we will need to move on, unfortunately, but that's also a good question. If you answer it, then others will be able to see your answer.
Thank you.
Okay, thank you very much for a fantastic talk. And we're now on to our last speaker, who can now share her screen. This will be Heather Kulik, who will tell us about computational discovery of transition metal complexes from high throughput screening to machine learning.
Thanks. So I think I'll shift gears a little bit from the first three talks you heard earlier, and tell you a little bit about how machine learning is advancing our understanding of how to discover new materials. And so where the motivation for this starts is the idea that if we want to go out and not just simulate materials to longer and faster timescales or simulate more of them, if we want to know and go out and discover new materials, knowing the right material for the job is really challenging. But if you take a look at where the right materials often end up being, it's often in these spaces of complex materials with metal centers with unpaired spins, and just the possible combinations of ligands and metal centers and ways we could arrange these materials. The space is so vast that finding the right material for a job, if we don't get told beforehand, oh, this is a privileged material, is a really challenging problem to solve. And so where machine learning can come in and play a role beyond conventional simulation is the idea that we might be able to build a language or an understanding of which atom matters most in a material in order to tell us how to design materials now atom by atom. And that's what my review covers, is sort of the relationship between conventional simulation techniques to do this, as well as statistical and machine learning techniques. If you're not familiar with this type of space of materials, you might ask, well, why should we care at all? And that's because if you look around to what are the most promising catalysts, they all have these types of materials. So a metal center with organic bits around. And so most of them are not the organic molecules you've been hearing about or the solid state materials here that you've been hearing about, but they're actually very complex combinatorially and challenging to describe quantum mechanically in terms of a unpaired spin on a metal center surrounded by typically tailored through trial and error ligands. Similar applications are found all the time in thinking about challenges in energy storage and in gas separations, including in periodic materials like metal organic frameworks and emerging single atom catalysts. So since the early days, people have been really interested in these materials because they seem poised to unlock and address a lot of outstanding challenges. And at the same time, all of the properties we'd like to predict in these materials are really hard to predict. You could think about wanting to be able to predict when a material oxidizes or reduces and how many redox steps are accessible. This is an experimental CV of some bimetallic complexes, and it's really challenging to predict why do some of these complexes have multiple redox events, whereas others have fewer. We can think about magnetic properties, things like a metal organic framework that changes its spin state and changes its properties when guest molecules are present in the pores. This would have applications in sensors. Optical properties of materials. So why are certain transition metal complexes blue shifted with respect to others? And ultimately, as I mentioned, what types of ligand tailoring can we engage in to enable catalysis? And so because the number of ways in which different ligands, oxidation states, metals, and spin states can all be combined is so large, these types of examples I've provided that people have lucked in on through trial and error are just one-offs in this really large space that machine learning has great promise to think about extending. And so the idea, machine learning is often presented as a new field to computational chemists, but people have been doing data-driven discovery in the space of transition metal chemistry for decades. And early examples of this might be things like the Tolman angle that told us about how stable complexes were based on cone angles of ligands. In the 2000s, this moved into three-dimensional interaction-based models and models describing the steric bulk of ligands, also using DFT-derived descriptors to predict why is one catalyst more active than another. And so what was different about this earlier time is that often these were on small data sets and built into linear models that often did not generalize well to new spaces. And so if you ask what has changed in the past 10 or so years is as we've moved into larger and larger data sets with kernel models, with neural networks that you've been hearing about, many times what's new is simply the size of the data and the complexity of the model. Many successful experimental works and computational works have just gone back and used very similar descriptors to the ones here to then build predictive models to predict which new catalyst should we synthesize experimentally and so on. So where do physics-based models fit into all of this? Well, as you've been hearing already, when you think about chemical discovery, we know that QM can provide insight in this type of space as well, allowing us to test really quickly, faster than we could experimentally, what material should we think about next. But QM is expensive, and to study the quantum mechanical properties of transition metal complexes, really density functional theory is the bottom rung of what we can afford. And so these types of systems, historically, people have thought a lot about hierarchical methods. So maybe we could go out and do some pre-optimization with molecular mechanics force fields, then maybe refine them with semi-empirical methods, refine further with DFT, and then pick a subset over which we carry out a couple cluster. However, these types of approaches that work really well in the organic chemistry and in the systems you've been hearing about today tend to fail in open shell transition metal chemistry. Because for instance, something like a force field that can predict really well, whether it's an analytical form or an ML model, can predict really well the progression from high bond order to low bond order. Properties of transition metal complexes change rather abruptly and non-linearly as we move between different potential energy surfaces. That being said, all hope is not lost. So while we can't just brute force apply low-cost methods in transition metal chemistry, this really motivates using data to improve the methods we have. And so it's worth noting that data-driven methods to improve physics-based models for transition metal chemistry have been around for a long time. This includes the so-called ligand field molecular mechanics force field, which can overcome more general approaches by taking parametrized information from experiment to be able to predict, say, spin transitions in transition metal complexes, as well as the D-block method of Friesner and coworkers, which enabled a data-driven way to parameterize corrections on top of DFT to do things like improve redox potentials. So where does ML fit into all of this? I wanted to introduce you first to the cousins of ML, earlier statistical applications, to put this all in context. And here is a figure actually from a book we published in partnership with ACS on machine learning in chemistry. And what I want to highlight here is that while neural nets have really come into the forefront of what people talk about when they talk about machine learning, even their development is not necessarily new. So these days we see widespread use of ML in chemistry. But there were earlier applications of ML in chemistry, including even thinking about how do we solve the Schrodinger equation with neural nets that date back 20 or 30 years. What has really changed in this time has been how much data is available and how quickly we can train these models. And so as an example of early work in transition metal chemistry, Gadi Rothenberg and coworkers recognized that exactly what I told you about at the beginning of my talk, that there's a really large combinatorial challenge to going out and exploring the space of all feasible ligands. And so when we do materials discovery with machine learning, we're trying to take advantage of the fact that we start from a discrete space we'd really like to explore, but the right answer we want to explore might be in a descriptor space. And ultimately our goal is to find an optimal material with the best possible property. And early days, they developed a series of ad hoc descriptors of both structure and QM based and applied some of the first machine learning models. This is from about 2004. And what they found was that with 500 experimental catalyst turnover numbers, they could do a better job of making a prediction of the turnover number with the nonlinear ANN than they could with a linear model. Not too much better, but a little better. And if you look at more modern implementations of ML in experimental catalysis, you'll see the same story. Is the flexibility of more complex ML models allows for better performance and better generalization, including over noisy data. So what has changed is an increase in the complexity of descriptors, data set sizes, and models. And what I'd say where we come into this is thinking about working with higher dimensional feature sets and larger data sets, not just actually choosing and crafting the descriptor set, but instead thinking about using the ML model to tell us what matters most. So complex models and what they learn allow us to identify structure property relationships, not know them beforehand and feed them into the model. And what this has enabled in this field is that now we can make predictions at DFT level quality of properties of open shell transition metal complexes in seconds. So we can fix the force fields that didn't work for predicting bond lengths. We can predict quantum mechanical spin states, something that would normally be very challenging to predict. We can predict redox potentials. We can predict things that we know are really closely related to reactivity, like frontier orbital energy levels. And we can do things like predict catalyst reaction energetics. And usually different representations can perform differently, but generally ones that have this atom-focused representation and allow the model to learn which atoms matter most perform best. And these are accomplished still because transition metal complexes are all quite large. These are accomplished still in data sets on the scale of thousands, much smaller than the regression sets that are often used for training force fields. And as I mentioned, one of the most valuable things that has come out of this is that we can identify which features of a material matter most, that atom by atom picture I showed on my first slide. And we can determine what we need to tailor and what we need to design in a material in order to go and find the next best material. So in practice, there's a lot of moving parts into all of these types of approaches. There's been a lot of work on representation development. There's a lot of work in thinking about how we generate data. In turn, all of us need workflows for training models. A key thing that's really important is to think about how do we know when the model is uncertain? So how do we quantify uncertainty? And then once we have all of those together, this is where the payoff comes in ML accelerated discovery. Either we can use the model where we know it's confident to do what's called model exploitation, or we can use the model and update it iteratively in an approach known as model exploration or active learning. This tells us where to go back into space to search for new materials. This is really important in chemical discovery so that we know how to go to the next step. And then ultimately, the result is that we get design principles and lead compounds. And so where does this lead us? This allows us to start to do things, not just accelerating the time scale over which materials are simulated, but accelerate the time scale to discovery, allowing us to explore spaces of 3 million unique materials to identify what are the best possible designs. This also allows us to work in iterative approaches, which are quite common, carrying out ML guided selection of new ligands. This is an example from the S Lab at Brigham Young University, where they started with one series of ligands, used an ML model to identify how they could improve selectivity generation over generation, went back and synthesized those materials, and so on. So I'd just like to finish, this is my last slide, by saying, well, what's left? What's left to do in chemical discovery? Because our challenges are different from thinking about just building ML accelerated force field development or anything like that. And that's, where does the data come from? How trustworthy is it? And how much do we have? And there are different ways to think about doing this. One is high throughput experimental synthesis. Another is thinking about extracting all reports from the literature and how do we know all those reports are right and trustworthy. But there's been a lot of progress there in recognition of compounds from published literature reports. And then finally, there's been a lot of advances in toolkits for chemical discovery that allow us to get better and faster about generating high fidelity data. And the result is that we can start to do things like extract design principles now, not just from DFT calculations, but from the extant knowledge of thousands of researchers. So I'd just like to conclude by saying, transition ML complexes are an example of a space in material science where the structure property mappings are really complex and hard to predict. And that has motivated since the early days data-driven models, but they often were quite simple. And what has really changed is that more complex mappings are now used. Advances have now made it possible that we can really rapidly discover new materials. And the next frontier on this, I think, will be continuing to get better quality and larger data sets to further advance this. And I'd just like to acknowledge some of my co-authors and thank you for your time and attention.
Wonderful. Thank you for a very interesting talk. And we already have a couple of questions and time to ask them. So the first one is, what is your strategy for feature selection?
So in my group, we've applied a couple of different things, but we tend to either what a machine learning model can do is we can either think of a neural net as one that is essentially performing feature selection through successive layers, in which case interpretation and analysis of the latent space tells us what the model has learned. That's one approach. A complementary approach is when we train a predictive kernel-based model, the similarity of compounds in the kernel space will inform predictions. And as a result, if we carry out recursive feature addition, we can identify from a subset of all possible descriptors the most important ones. And that's what I was showing earlier on this slide. And so in that case, the only challenge is that the way in which we add features could be sensitive to things like train test split or to the order in which we add them, and so those just need to be considered. But we've generally found these to be robust to data set size as long as the data set is sufficiently diverse. And so here we stop adding features when they don't improve the predictive performance of the model.
Okay, great. And there's another question, which is, it appears that for homogeneous transition metal catalysts, spin properties are important, but these require higher level of quantum mechanics. How much data generation, quantum mechanics, is needed to get good training data for descriptor selection?
Yeah, so that's an interesting question. In these materials, what we've done a number of things thinking about this. One key thing to note is that a lot of the organic ML world pre-optimizes structures with semi-empirical and molecular mechanics. That in particular is particularly limited in transition metal chemistry because the molecule won't stay together. And the same stationary minima don't exist in these lower level theories. So just getting a single point, say with a high scaling method, is not so hard. It's more about getting an optimized structure. So that's one piece. But we've observed recently that things like these feature maps of the most important features for predicting properties turns out to be extremely invariant to the level of theory employed. So while absolute properties vary significantly, these pie charts don't. And so that's one promising avenue. Another promising thing to think about is identifying when lower level theories are trustworthy and when they're not. That's another avenue that's been explored, is how do you detect when low cost methods are inaccurate, I think is important for all of machine learning. As we're ingesting data, we're inheriting the bias of the underlying method. So in terms of how much data is needed, it depends on the prediction accuracy you're going for, but we've identified that using a consensus, a family of around 20 different methods all at once allows us to robustly predict experimental results even when spin is known to dominate. As an example of how you go beyond what I had a chance to talk about today.
Okay, great. Well, that seems to be it for our questions here. So I want to thank our guest editors and our speakers and all the other authors in this thematic issue. And I also want to thank the audience here for attending the Chemical Reviews Thematic Talk Series. And I hope that all of you will join us again on December 3rd for a symposium on gold chemistry. So we do one every couple of months on different topics that are covered in thematic issues. So thanks to everyone, especially our speakers who gave, I think all of them gave fantastic talks.